All right, so let's take a look at today's lesson. We're going to be looking at the second derivative test. Before we start that, I want to talk to you a little bit about what we've done in the unit so far. This unit's focus has been on the derivatives basically describing the position, like in a lot of different ways, right? We've learned about increase, decrease, how it describes the original function. We've learned about relative maxes and mins. We've learned about concavity. We have a lot of information that the derivatives can give us about the position function. Now, today's topic, second derivative test, actually is a test that will find us relative extrema. Okay, so my very favorite test to do that is the first derivative test. I don't want to hurt the second derivative test feelings or anything, but I really like the first derivative test. It's easy. Let's remind you what it is. If you recall, first derivative test. So we find the first derivative, we set it equal to 0, we find the critical numbers, the stationary points, and we also find the singular points where it's undefined. Right? We find both of those. We put them on a number line. We do a sign analysis. And when the derivative changes from increase to decrease, or from positive to negative, so the function's changing from increase to decrease, we have a relative maximum and so forth. Right, that test, pretty straightforward. Of all the tests that we're going to learn, and we will learn quite a few, I think it's one of the easiest ones. It's pretty straightforward. You do this, you put them on a number line, then you analyze the number line. It's great. Sometimes, though, it's not possible to use that test. And typically the reason it wouldn't be possible to use that test is because, well, the AP guys love the second derivative test. I'm just going to say they love it. So they like to come up with ways where you're not given the equation, you have no idea what the signs of the first derivative are, so you're just kind of left out there with this abstract information. So that's why it's really important that we learn the test. It's likely you will encounter it on the AP test. Again, just because it's a higher level of thinking. I mean, it's not really easy like the first derivative test, and a lot of students have trouble with it. So we're going to kind of walk through it, make sure we're okay. So I guess it probably doesn't surprise you that the second derivative test uses the second derivative in the test. So we've got to basically find suppose that the second derivative is continuous. Yeah, it needs to be continuous because we're going to use it. We're going to use the second derivative. So here's the criteria. The first one is basically if the first derivative at a certain location is 0. So we do have to have some information about the first derivative. We need to know what the zeros are. Notice that it is not giving me any opportunity for the first derivative to be undefined. We're not looking at that kind. Right? We're not looking at the singular points, because if the first derivative is undefined at a point, the second derivative probably is too. So it really is a little bit limited. The test is a little bit limited in that it will not find the relative extrema at singular points. So it's a little bit of a problem, but not too much. So we see where the first derivative is 0, and when the second derivative is negative, we have a local max. When I very first learned this test, I tried to just straight memorize it, and it was so confusing because you have the second derivative being negative, which to me means like minimum, right? Yet it yields a maximum. So I really want us to understand what's going on with this rather than just straight memorizing it. So let's think back to concavity that we just did. So if the second derivative is negative, that means that we're concave down, right? And concave down, so we're concave down. And if we're concave down, it would make sense that that extrema would be a relative maximum, right? Because that's basically what is generated when we're concave down. That's really the only thing that could happen would be a maximum. So that's why we have a local maximum there. So I want you to understand why. Why is it a local maximum? That's why. Okay? So our second one is if the first derivative is 0 and the second derivative is positive, then we have a local minimum. Again, hopefully that makes sense. So if the second derivative is positive, that means we're concave up, right? And so concave up looks like that, and that would make sense that there would be a local minimum there. We okay with that? Okay. Then the third part is if the first derivative is 0 and the second derivative is 0. the test fails. Another reason why it's not like my first choice is because it could fail. So there we go. That is the test. That doesn't mean, basically when it fails, it just means it doesn't give you the information that you need. Who knows whether it's a relative extrema there or not. You would have to find another way to figure that out. Alright, so what I would like to do is, on the first example for this technique, we're just going to use an equation. Now, to be perfectly honest with you, if I was given this equation and asked to find the relative extrema, I would do the first derivative test. Okay, I would do the first derivative test. It's easier. But I want to show you how the second derivative test works on an equation, so that will be like your introduction to the process. How does it work? And then we will get to a problem that's much more abstract that we can't use the first derivative test on. All right, so let's do this. So what do we need for the second derivative test? Well, we need the first and the second derivative. So let's go ahead and find them. So f prime of x is going to be 15x to the fourth minus 15x squared. Then we have f double prime of x is going to be 60x to the third minus 30x. Okay, so we have our first and second derivatives. So our first thing we're looking for is if the first derivative is 0 anywhere. So let's do that. Let's set the first derivative equal to 0. And let's see what's happening. So I'm going to factor. And I'm left with, okay, so x could be 0 or x could be plus or minus 1. Okay, so there's 3 places to check. Now, I think the very easiest, quickest thing for you to do to find out our second part, the sign of the second derivative at that x value, is to simply substitute them into the second derivative. I really think that's the fastest way to do it. Is that the only way to do it? No. You could do a sign chart if you want to do, or other things, but I really think the fastest way would be to simply take these values and substitute them into the second derivative and see what happens. So let's do that. So f double prime of 0 is 0 minus 0 or 0. Oh, okay. Well, we just looked at item number 3. If the first derivative is 0 and the second derivative is 0, then the test fails. And we are only asked to use the second derivative test, and we're supposed to find where the x value, where the relative extrema are. So at x equals 0, the test fails because f prime of 0 equals 0 and f double prime of 0 equals 0. So that's why it fails. We're done. We can't do anything with that. Alright, so let's look at x equals 1. So we'll go over here, find the second derivative value at 1. Let's see, what do we get? We get 60 minus 30, or 30. Okay, so we get positive. Okay, so let's analyze this. So first derivative is 0 at 1, and the second derivative is positive. Positive means we're concave up. Since we're concave up, there's a relative minimum there. Okay, so we have a relative minimum because f prime of 1 is 0 and f double prime of 1 is greater than 0. Now let's talk about this justification. Notice how there's 2 parts of the justification, and I really want to highlight, I am not writing f of x here. Notice, I am saying what the x value is. It's much clearer if you do that instead of just saying f of x. Could you get away with saying f of x there? Sometimes. But why chance it when we're actually looking at a particular location? Just say f of 1 equals 0. Another thing that I want to caution you about is here, we've said, I said f double prime is positive. I would really encourage you to do that rather than putting the actual numeric value there. Because if you put the numeric value there and it's wrong, you'll lose the point. Okay? So I'm not saying what the numeric value is. Maybe I made some kind of arithmetic error and it was actually 20 and not 30. You know, maybe I did something wrong. Why chance it? Just say it's positive, because that's all the test wants anyway, is whether it's positive or negative. So just some advice to you. I would do that just to be sure that you don't make an arithmetic mistake and lose a point. All right, so now let's look at x equals -1. So let's sub -1 into the second derivative, and we get, what, -60 plus 30, or -30. Okay, so it's negative. Okay, let's think about it. So second derivative negative means concave down. Concave down means relative maximum. So we have a relative maximum because f prime of -1 is 0 and f double prime of -1 is less than 0. Again, just be safe, right? Whether it's positive or negative, don't commit to an actual value. Yes, ma'am. Well, that's true. You're giving more information than's asked, and whenever you do that, you have to be very cautious because you're exactly right. If you give more information and it is wrong, you lose the point. I discovered that, you know, as a grader, as a reader. Yeah, I was like, oh, I wish you hadn't written that. You lost the point. So yes, that's very good. You really should not furnish more information than you have to. Yes. Yes, sir. Local and relative are interchangeable. You can use them either way. Okay, so how are we on this? Are we okay with this? Okay, so now let's go to a problem more like you might see on the AP test. Is on our second page. This is a problem that was designed to where you can't do the first derivative test. Okay, I like the first derivative test, right? It's easy. But you can't do it. So let's see why. Let's see why you can't do the first derivative test here. So, suppose that the function f has a continuous second derivative for all x. Okay, they're telling us that we have a continuous second derivative. Wonder why? Well, probably because we're going to need it, right? They usually don't say things that you aren't going to necessarily need, so it's like, oh gosh, that's probably means second derivative test. But we'll keep reading. And that, so we have some function values. We have a function value, a derivative value, and a second derivative value. Definitely not enough information to get signs on a sign chart. One value would not do it. Okay, so, all right, let's keep going. So let g be a function whose derivative is given by, oh, that is great. Look at that. G, it's got an f inside of it. It's got like x squared. It's all jumbled together. Oh, it's fantastic, right? So some students might look at that and say, oh my gosh, I can't do this, but that's not us, right? We're going to say, this is great. We're going to keep going. So, all right, that's great. Do we have local max or local min? Well, okay, first derivative test is out. Can't do the first derivative test, so let's focus on the second derivative test. And really, we have had this memorized, right? From our formula quizzes, we have it memorized. We're going to be able to do this. So what do we need? We need to know if g prime of 3 is 0. That's what we need to know, right? That's the first part, is that the first derivative at that location must be 0. So let's just tackle this little thing. So g prime of 3 is 3 squared minus 9 times 2 f of 3 plus 5 f prime of 3. Okay, so that's the work that we would need to show. Alright, so here we have 3 squared minus 0. That's really great, but I want to caution you. Do you remember in the past when we had basically 0 times something and we thought, oh, it's just 0, and it didn't work well for us? Remember that? Like 0 times d and e. Did that work well for us? No, because d and e really doesn't care about the 0, right? Or 0 times infinity? Not so much, right? So I'm just cautioning you to not just jump to it's 0. We'll just look at it though. So do we have values for f of 3 and f prime of 3? Yeah, they're just numeric. So we are pretty safe here to say that g prime of 3 is 0 because 0 times whatever number that comes out to be is a 0. Are we okay with that? All right, so g prime of 3 is 0. All right, so our first criteria of the second derivative test is met. So let's look at the second criteria. We need the second derivative. Yay! Right, we're going to take the second derivative of that. Oh, that's going to be great. So let's look at it. Oh, it's a product. Yay! So FG plus FG, first things first, second things second. So here we're going to tackle it. We need a little bit of room. Give yourself a little bit of room, okay? G double prime. So the derivative of the first piece right here would be 2x. Copy paste the second piece. 2f of x plus 5f prime of x plus, okay, so copy paste the first piece, which is x squared minus 9. Take the derivative of the second one, and it's like, oh my gosh, the derivative of that. But really, it's not bad, right? Because the derivative of f is just f prime. You don't really have to do anything except put like a little prime there. So it's not too bad. So 2f prime of x plus 5f double prime of x. Okay, there's our derivative. So our test requires us to find the sign of 3 at the second derivative. So let's sub in a 3. So we want to know what g double prime of 3 is. So 3 times 2 is 6. Then we have 2 times f of 3 plus 5 times f prime of 3 plus 3 squared minus 9 times 2f prime of 3 plus 5 f double prime of 3. Okay, that's the work we need to show. Now, let's just see right here, can we safely erase all this? Is this all going to be 0? Because I have 9 minus 9, that's 0. These are just regular real numbers, right? We're good. That's all 0. So that's good. So let's just focus on this part right here. So g double prime of 3 is going to be 6 times, let's see, 2 times f of 3. So f of 3 is negative 4. So 2 times negative 4 is negative 8 plus, okay, so 5 times f prime of 3. F prime of 3 is 1, and 5 times 1 is 5. Okay, we're getting close. So what is that? Negative 3 times 6, so negative 18. Okay, so we have the second derivative is negative, which means concave down, right? Which means we have a relative maximum. So a relative max at x equals 3 because why? Because g prime of 3 equals 0 and g double prime of 3 is less than 0. I still would like for you to be cautious. What if I did that wrong and it's negative 16? Just say it's less than 0. Okay, just be cautious. Unless you are the best person at arithmetic and multiplication division that is known to man, like your computer in your head, I would really recommend that you just say it's less than or greater than 0. Okay? How are we? All right, great.